Well, thanks for joining me. Today, this lesson will be about double replacement reactions. Now, in previous lessons, we learned to classify synthesis reactions and recognize their format. Element A plus B goes to AB, and things such as that. We learned decomposition was AB goes to A plus B. Those are relatively easy to identify. Single replacement was an element A plus a compound BC turning into a compound AC and an element B. In order to do a single replacement reaction, we used the activity series to predict if those reactions would occur. Remember, on the activity series, if you are ranked higher up, listed higher, you can replace the element lower down. And it's always, can the single element, in this case A, replace its counterpart? In this case it would be B. So we would be seeing that A is listed higher up than B on the activity series. The next type of reaction is called a double replacement reaction, and this involves two compounds, AB plus CD, turning into AD plus CB. Now, there are only three ways that a double replacement reaction will occur, and these three ways are called driving forces listed at the bottom of the page. So, the new combinations AD and CB must either be water, literally H2O, and the reaction will occur. Or if one of them is a gas, the reaction will occur. Or if one of them forms a solid, also called a precipitate, the reaction will occur. And we're going to address that in much greater detail here in just a moment. The other reactions that we talked about, neutralization is the reaction between an acid and a base that makes a salt plus water. It's really nothing more than a double replacement reaction where water is the driving force. Combustion of hydrocarbons were a special class we talked about. When you burn a hydrocarbon in oxygen, it produces carbon dioxide and water. Just to remind you, when you balance those, you do that in the order CHO, and that'll make it much easier for you. And the last class of reactions were called polymers, or polymerization, where a polymer is made from many monomers. And in class, we listed multiple examples of polymers. So, with all that reminder, let's now focus in on double replacement reactions and see if we can make some sense of these things. Okay? So, I've got a reaction here on the bottom. It says silver nitrate, and that's a colorless solution, and potassium chloride, a colorless solution. When you add them together, you get this white-looking solid material called silver chloride. Now, there were actually, what's going on here, if we look at the reaction at the bottom, the silver and the potassium are switching places. And when they switch, one of the new combinations is potassium with nitrate, and the other combination is silver with chloride. Now, I have to figure out which one of these forms the solid. So in order to do that, I'm going to use the solubility table. So we're looking at potassium nitrate and silver chloride. So let me introduce you to the solubility table. Here it is. Looks a little bit like Battleship, where if we say potassium, see here's potassium, and then we find nitrate, nitrate comes down from the top, it lands right here, and it says AQ. Well, that means it is aqueous. Now, the other thing that we had was silver chloride. So here's the silver, and the chloride is located right up here. So when we bring those two together, we see the letter S, which on the legend says that is a solid. That's how I know that the silver chloride is my solid and the potassium nitrate is aqueous. Okay, let's go back up there a second. Alright, so here we are. So again, the potassium nitrate was aqueous, silver chloride was solid, and the fact that it formed a solid is why that reaction occurred. Now, you may be asking, when will the reaction not occur? Well, if both combinations, potassium and nitrate, the new combination, and silver chloride were both aqueous, there would be no reaction. It would just float around in solution. Let's look at another one. So in this example, we're going to be looking at a clear liquid dropped into a clear liquid, and it forms a yellow solid. That tells us that alone that the reaction is going to occur. So what did we mix? Well, we mixed solutions of lead chloride and potassium iodide. Now, word equations are nice, but I would prefer to use chemical equations to explain this. So here's the lead chloride and the potassium iodide. And that's the formula of each. Now, when they mixed, the ions were floating around. Now, if they stayed the way they are right now, lead with chloride, potassium with iodide, there's no new combinations, so there would be nothing happening. And there's no chance that the lead and the potassium will get together because they're both cations, positively charged, and they will repel. Likewise, the two anions, chloride and iodide, are both negatively charged and would not get together. So what must happen is the ions, the cations, switch places. Now I have two new possible combinations: potassium chloride, KCl, and lead 2 iodide, PbI2. Now, I have to figure out which of these is going to form my solid, the KCl or the PbI2. Now, without knowing, I'm going to look at my solubility table. So let's click on that solubility table. Now, let me erase what we have on here so as not to confuse you. So let's start with potassium and chloride. Now, the one thing you want to notice is all the potassiums are aqueous. So maybe that's a pattern. It's aqueous. And chlorides are almost always aqueous, but the one we're focused on right here, potassium chloride, is definitely aqueous. Okay? So we'll remember that one's aqueous. Now, because we saw something, the default is the lead iodide must be the solid. But let's just confirm that. Here's the lead. Here's the iodide. Run those two together, and right there it says S, and S on the legend means solid. So that is how we know which one forms the precipitate. Okay? Let's go back again to where we were. So using our solubility table, we determined the aqueous for the KCl and the solid, and we could put PPT because it means solid coming out of solution, for the lead iodide. We could then balance that with coefficients. It's a little bit hard to see, so I cleaned it up over here, and I added down here the PPT and AQ. Now, I do have two I's here and only one here, so I should have corrected that and put a 2 here, 2 Ki, and 2 KCl, and at that point, now we have 2 potassium, 2 potassium. Now that's a balanced equation. Okay? All right, let's do another one. See if this makes a little more sense. And actually, we're going to look at the same one, but we're going to think about it a little bit differently this time. So we're thinking about the same reaction we just looked at. So we were reacting lead chloride and potassium iodide. So lead chloride in solution makes the ions Pb2+ and Cl1-. Potassium chloride in solution are the ions K1+ and I1-. Now, when they get together, if they stay the way they're shown here, there's no reaction. So we said they must switch places. Now we get new combinations, and of course we have to look up the solubility of those. The KCl is a possible one, and the PbI2 is the other one. Using the solubility, we determined that the lead iodide was solid and the KCl was aqueous. We can go ahead and balance that. Now, we've got ions here floating around on the reactant side, lead and 2 chlorides. So they're floating around. I have 2 KIs. They're also aqueous. That means they're floating around. So all of this stuff is in my beaker at the beginning, floating around as ions. If I could see, if I were Miss Frizzle or had the Miss Frizzle glasses, that's what I would see. When they move over and react, we said that there's going to be some new combinations. Now, I went ahead and balanced this with coefficients. So there's actually would be 2 KCl's here if you took the time to balance it. That's why I have 2 K pluses and 2 Cl minuses. And of course, I would have the PbI2, and there'd be 1 Pb and 2 Is. Now, when I looked at the solubility chart, I realized that the solid is the lead iodide. So notice how the lead and the two iodides came out of solution and they formed a solid that I can now see. And they sit on the bottom. That's the yellow solid that I would have seen. And the potassium and chloride, they remain floating around in solution. This reaction clearly occurs because a solid is formed. All right, let's look at another one similar to this. Okay. We have here a potassium carbonate reacting with barium chloride, and it says it could produce potassium chloride and barium carbonate. Now, what was happening was the K and the Ba switched places. So that's how the Ba ended up with the carbonate and the K ended up with the Cl. We get the formulas, then we looked at the solubility chart. Now, from the graphics, this first one is colorless, this is colorless, and if you look really carefully in here, you can see some white solid being formed. And if you remember, potassium is always soluble and chloride is almost always soluble, so that's why this one is aqueous. And if we looked at that chart, and I'll go one more time, let's see what barium and carbonate says. So I'm going to go down here to the chart. I don't have a link to it, so it's going to take me a second. All right, so here we have barium, right up here where the cursor is, and carbonate. And it says, here's the carbonate right here, and it says I. Now, I on here means insoluble. That's a solid, okay? Every chart is going to look different. Notice here that I means solid, SS also means solid, and S means aqueous. It refers to soluble, okay? So depending on how that chart is listed, right, here I is insoluble, SS slightly soluble, S soluble. If it is, and what that means is, again, insoluble means a solid, soluble means aqueous. So your chart could look like this that I give you on the test, or I could be nice and give you one that looks like this, where S refers to solid, AQ aqueous. Okay? You just have to read the legend and know what it means. All right, let's go back up here where we were, and we'll do a few more examples of this. Okay? All right, so we just took care of that one, and now let's try another one. Let's use this. We talked about how would you predict, how would you prepare potassium nitrate using a double replacement reaction? Well, what we know is potassium nitrate is the product, KNO3. And we know, based on the law of conservation of matter, what you start with, you got to end with. So there must be some potassium and some nitrate at the beginning. Remember, a double replacement takes the form compound plus compound makes compound plus compound. So I know there must be some K and some nitrate here. And now what I need to do is figure out what else could go there. Now, we said there were three driving forces. The first driving force was formation of water, H2O. Now, H2O is nothing more than an H plus and an OH minus. So what I could do is this. I could make water my driving force and work backwards. So basically, the potassium and the hydrogen have to switch places so that the potassium ends up with the, well, when it breaks apart here, it's really going to look more like this, HOH. So the potassium and the hydrogen are switching, so the potassium ends up with a hydroxide, and the nitrate is going to be combined with a hydrogen. So I'm going to combine potassium hydroxide, KOH, and nitric acid, HNO3, and I will indeed produce potassium nitrate. So what's happening is that switch, and that gives me my new combinations of water and potassium nitrate as shown. little bit harder to do that type problem, but I think you're up to it. You can do that. Let's try this. What if I started with calcium nitrate, and what I want to do is combine that with potassium hydroxide? Well, if I switch the cations, the potassium and calcium, if I have these guys switch places, I end up with potassium nitrate and calcium hydroxide. Now, in order for this to occur, I need a driving reaction. Water was not produced. And I'm going to tell you neither of these is a gas, so one of these has to be a solid for this to occur. Now, maybe you remember potassiums are always AQ, so that's not going to be the problem. That's not going to fix it for me. So I need to look up calcium hydroxide. So we'll go down. Again, I apologize I didn't put a link on here. It makes it a little bit awkward, but we'll go down till we find that solubility table. Here we go. So let's go to this one here. We like this one right here a little bit more. So we're looking at potassium with everything is soluble. So potassium nitrate's AQ, but the other one we had there was lead hydroxide, maybe? Lead hydroxide. And that's a solid, so that would work. If it were calcium hydroxide, that's slightly soluble. That also would be meaning it's a solid. Everything on gray here is going to be a solid. Okay? All right, let's go back up there because I didn't write down what we were looking at, and I lost my train of thought as I'm clicking through this all. So in this case, it was calcium hydroxide, which is a solid. So that would indeed work to give me the reaction. Now, I then have to filter out the calcium hydroxide, and then I have to remove the water by drying this to get my potassium nitrate, if that was my goal. Okay? So lots of ways we could do these reactions. Let's try another one here. Let's see what comes up now. Let's predict if a reaction would occur if we combine. Now we're using word equations and double replacement. We're combining a lot in this question. Predict if a reaction will occur if you combine aqueous solutions of iron chloride and aqueous sodium carbonate. So I'm taking here and reacting iron chloride and sodium carbonate. I want to go ahead and get some formulas here, so I'm going to go ahead and do that. And again, hopefully you remember your nomenclature and you could get to the formulas. Now, I see a compound and a compound reacting, so they're going to have to get a new combination. They can't stay the way they are. The cations are going to switch places, and now I have two new combinations. I have sodium chloride, NaCl, and iron 2 carbonate, FeCO3. Now, your own experience tells you that sodium chloride dissolves in water, AQ. Okay, you know that. Now, I'm not going to click on because I don't want to waste the time, but if I were to click on the solubility table and I were to line up iron and carbonate, I realize that almost all carbonates form a solid. So this reaction will occur because it has the driving force, the formation of a solid. I guess it's here. Let's look it up. Iron carbonate. So I find my iron. We had iron 2 with carbonate. Carbonate's up here. And where they come together right here, S on this one says solid. So that one is not, is going to form a solid. That reaction will occur. So then, and sodium chloride is soluble, if we would have looked. So then I can go ahead and add AQ there. That AQ means it is soluble. And the solid, or PPT, after the iron carbonate says that reaction will occur. I would then go ahead and add my pluses in between it, and for good measure I would balance it. I notice I have 2 sodiums on the reactant side, so I need to put a coefficient 2 on the product side. And then I have 2 Cl's on the product side, and I have 2 on the reactant, and from there it's all balanced. Alright, I hope this is making sense. I'd like to do one more example for you. so that you can see it. I'm not worried about, at this point, complete ionic equations. We'll address that in our unit on solutions, so you can ignore the bottom line. Let's try this one here. It says aqueous barium nitrate reacts with sulfuric acid to yield barium sulfate precipitate and nitric acid. So we got barium nitrate reacting with sulfuric acid to yield barium sulfate and nitric acid. So I write a word equation. Now I'm going to write a chemical equation, writing down the ions that are formed from each of these, and then coming up with the equation for each of these. And again, this is the part that for some of you is going to take a while for you to figure out, to remember how to do. Okay? But now that we've got them, we hopefully recognize that's a double replacement reaction. Now, we're told that the barium nitrate is aqueous. We'll go ahead and balance this as well. Put those coefficient in there, the 2 in front of the nitric acid. So barium nitrate's aqueous, and sulfuric acid is also aqueous. Aqueous means it dissociates into ions, so it'll make 1 barium and 2 nitrate ions, and I'm going to put those in solution. Sulfuric acid also says it's aqueous, so if it's aqueous, that means it makes ions, 2 protons, and a sulfate ion. They're going to float around in that solution. That's what it looks like at the beginning. Now we're told it produces a barium sulfate precipitate. That means that one is a solid. So we might break it apart, but understand that it's not broken apart. Here's the nitric acid if we want to put it in. Because the barium sulfate forms a solid, it is going to sink to the bottom. And now we went from the invisible to the visible solid barium sulfate on the bottom, and the 2 H's and nitrate are floating around. This is what is occurring in a double replacement reaction. All right, I've gone about 22 minutes, so I think that's as far as I want to go in this particular video. I would just remind you of a couple things. When looking at a single replacement reaction, it's an element and a compound, and an element and a compound, where the single element, in this case magnesium, is going to try to replace its counterpart, copper. And magnesium is ranked higher on the activity series. So just to remind you, a single replacement reaction, we're looking at activity series. For a double replacement reaction, what we just went through, I call it kind of wife swap, where the 2 cations switch places and get 2 new combinations. So it's a compound and a compound reacting to form a compound and a compound. And the only way these will work is if a driving force is present. And the 3 driving forces are formation of water, a gas, or a solid. And we're going to use a solubility table to determine if it forms a solid. Okay? That's the big idea with double replacement reactions. Okay? We've seen the general form before. I will provide for you an activity series like this. I will also provide for you a solubility table. Now, I have undecided if I'll give you one like this, where you have to pay attention to the legend, where I means insoluble, S means soluble, which is code for I is solid and S is AQ. Or maybe I'll be nice and give you one where it says S is solid, AQ is aqueous. In either way, be prepared, because you're going to have to know how to use that. If you want to be safe, print off the one that's on the screen right now, because that's a little bit easier for most students to understand. All right, thanks for joining me. This will be the same lesson that I give in class tomorrow. Take care. Bye-bye.